So for this example, we're looking at a university. They've done a survey and they're concerned at the results. So they found that when they asked students about their exercise activity, that 60% of them said that they don't exercise at all. 25% that they reported that they exercise sporadically, and 15% reported that they exercised regularly. And so the university is a little bit concerned by this. And so they implement a new health promotion campaign. They run it for an entire year. And at the end of the year, they wish to sort of evaluate the success of their campaign. So has the distribution in exercise activity changed? So they asked 470 students and asked them whether they don't exercise at all, if they exercise sporadically, or if they regularly exercise. And these are the observed values. They've asked us to conduct an appropriate chi-squared test with 95% confidence. So in this case, because there's only sort of one categorical variable, the amount of exercise, the appropriate test here is going to be a chi-squared goodness of fit test. Okay. And we have our observed values here, and the expected values we can sort of work out, okay? So we're going to use the previous year's sort of probabilities or proportions to sort of give us a guide of what we would have expected if there was no change in exercise behavior. And then we're going to see how much our observed has changed from the expected behavior. So it says that 60% report not exercising regularly. So if I do 0.6 times the total, which is 470, just work that out on my calculator here. So 0.6 times 470 gives me 282. Okay. So if the proportions were the same as they were in the previous year, in this group of 470, I would have expected 282 of them to say that they didn't exercise at all. Okay. And I can do the same thing here for the sporadic exercise, right? So it said we did 60, 25% reported exercising sporadically. So 25% times the 470 gives me 0.25 times 470 gives me 117.5. Okay. And last but not least, the 15% that report exercising regularly, so 0.15 times 470 gives me 70.5. Okay, so those are my expected values. Okay, and so again, usually we can work out our test statistic as the observed minus the expected squared divided by the expected. And you could totally do that for those three cells. But I'm going to just walk through how to do that on a calculator and how to do it in R. Oh, I guess before I do that, I should just write down really quickly the null and the alternative hypothesis here. So the null hypothesis is that the distribution in exercise behavior, wow, I cannot spell, exercise behavior is the same now as it was before. Okay, so mathematically speaking, that would mean that, you know, the proportion with no exercise is 60%. The proportion who have sporadic exercise, oops, I'm just making up some letters here. Sporadic exercise is 25%, and the proportion with regular exercise is 15%, something like that. Okay. And then our alternative hypothesis is that the proportions differ from those given proportions. So the distribution in exercise behavior, I did the same thing. I really don't know how to spell exercise for some reason. Exercise behavior is different than proportion of no exercise is 0.6, the proportion of sporadic exercise is 0.25, and the proportion of regular exercise is 0.15. Sometimes they'll talk about, at least one of these proportions being different. Because in theory, right, it could be that, 15% still regularly exercise. It's just the proportion between no exercise and sporadic exercise that's changed, or vice versa. Maybe the proportion who don't exercise at all hasn't changed, but maybe we've convinced more people from in the sporadic group to exercise regularly. At least one of these proportions is different. Maybe I'll even write that in here. At least one of these proportions is different. Okay. So let's just flip over to R, and we'll walk through how to do that in R. Okay. So in R, we have to go through and enter in the data. Okay. We don't need a matrix anymore because we've just got sort of one variable here. So we can just go through and enter in a list of numbers. So maybe I'll say something like observed. And then I'm going to assign the values of observed. So 255, 125, and 90. So again, make sure you don't include the total value, just the three numbers that are observed in the table. Okay. You also, in R, rather than having a list of the expected values, it actually wants a list of the sort of hypothesized proportions. So I'll call those props or something for proportions. Okay. And the hypothesized proportions are 0.6, that's our 60%, 0.25, that's the 25%, and 0.15. And so it's going to want those. Okay. And then you're going to do your chi-square dot test. You're going to put in your observed values, and then you're going to say that P is equal to your props. Okay. And when it does that, it's going to spit out your test statistic, which is your chi-squared, and in this case, it's going to follow 2 degrees of freedom and your p-value. So let me maybe just write that into here. So it says that our test stat, okay, is 8.4574. Okay. And this is going to follow a chi-square distribution with 2 degrees of freedom. Now, just to be totally clear, the chi-square goodness of fit test, to get the degrees of freedom is always the, oops, you can't see what I'm writing. To get the degrees of freedom, okay, that's one way to do it. To get the degrees of freedom, it's always the number of categories minus 1. So in this case, there was 3 different categories, the no exercise, sporadic exercise, or regular exercise. So they did 3 minus 1 to give us 2. So the degrees of freedom is slightly different for the goodness of fit test as opposed to the test of homogeneity or the test of independence, where we're doing number of rows minus 1, number of columns minus 1. Okay. So there's our chi-square distribution with 2 degrees of freedom. There's our test stat, and the p-value is the area to the right. And it tells us here that our p-value is 0.01457. Okay. And so from that, we can go through and make a conclusion here. Our p-value is definitely less than our alpha, which was 0.05, because they asked us to do this test with, let me get this out of the way. They asked us to do this test with 95% confidence, right? Okay. And so my p-value is less than my alpha, which means that I'm going to reject the H naught. Okay, we have significant evidence here to say that the exercise behavior is different from the 0.6, 0.25, and 0.15. So I'll just say there is significant evidence to suggest the distribution in exercise behavior is different from the previous year. And you could go through and look at the actual proportions in that table to figure out, you know, which groups actually did it end up influencing. Was it all the groups that we shifted everyone to exercising a little bit more, or, you know, many people to exercise more? Did it do the opposite and people are exercising less? Or, you know, who did we sort of shift around? So you could go through and look at this table in more detail to figure out, you know, what happened there. I should go through this quickly and show you how to enter it into a calculator so that you can get your test statistic. So again, we don't need the matrix button anymore. Matrix is only when we've got a table that has some rows and some columns. So instead, we're going to go into our lists. So remember, to get to those, we do, let me just move this over here. So remember, to get into those, we do stat and then edit. Okay. I'll just clear out whatever I had here. Okay. And so you're going to put the observed values in list 1. So I'm going to put in 255 and then 125 and then 90. So I'll put the observed values in list 1. And then I'm going to go through and put the expected values in list 2. So the expected values here are 282, 117.5, and 70.5. Okay. So once you've got your observed in list 1 and your expected in list 2, you're going to go to stat and then over to tests. And again, you're going to go all the way down, okay, until you see chi-squared test. That's, remember, for the test of independence or the test of homogeneity when we have some rows and some columns. If you only have one variable, you're doing a goodness of fit test, what we agreed on. So you're going to choose the goodness of fit test. We put our observed in list 1. We put our expected in list 2. And then you actually have to tell it the degrees of freedom. So remember, the degrees of freedom is the number of categories minus 1. So in this case, there's sort of 3 categories minus 1 means my degrees of freedom is 2. And then we'll press calculate. Okay. And it gives me my test statistics. So that's the same thing that I got before in R. Follows a chi-square distribution with 2 degrees of freedom. We told it that. And then it's got our p-value, which is the same p-value that we got before, I think, right? 0.01457. Okay. And then again, you'd make the same conclusion. So hopefully that helps show you how to go through and work out the test statistic for a goodness of fit test. It is slightly something you have to pay attention to. If you're an R user, remember you enter in these proportions. If you are a calculator user, you're going to want to enter in the expected values, the whole numbers. Often in these tests, rather than giving you like specific proportions or specific percentages, they'll just say that they're equally spread across the different values. So, you know, that's not the case here, but if it was, I would say, oh, there's 3 categories. If the null hypothesis that it was equally spread, that would just mean I'd have a third in this group, a third in this group, and a third in this group. So you could treat that as 1/3 or 0.333 or whatever you want to do. So I think the ones in the homework have you often doing it where they're testing that the numbers in each group are the same. But again, you can choose sort of any expected values based on the context of the problem. They may give you some sort of alternative thing that we might expect. Good.